In fluid mechanics, we have seen a very famous equation which is called a continuity equation. This continuity equation is a backbone of fluid mechanics. We will derive this equation, continuity equation, by the theory that we already developed. If I just expand the continuity equation, it will look like this: partial rho by partial t, partial by partial x, rho u, partial by partial y, rho v, partial by partial z, rho w is equal to 0. Here we have written this equation where there are more than one dimension. The independent variable, when it is x, y, and z, then this is called the dimension. So here you can see that this is x derivative, y derivative, and z derivative. So if I just remove these two terms, then you get the one-dimensional continuity equation. So our idea is to use our previous knowledge on the uh, advection equation and convert that into the continuity equation. So let me just write the first equation from where we started the equation, advection equation, in general form. Maybe I should write not the advection equation, but I should write its general form. That will look like this: flux. There should be a flux over here, flux, which is a function of q, and it is equal to 0. What I do if I just replace q with density, then this equation becomes partial rho by partial t, partial by partial x. Then the flux will be a function of density only. Then afterwards, if I say that, for example, the flux, the quantity that is entering, for example, if I have a pipe and the quantity that is entering is density, and it has some velocity, for example, if it is constant, then that flux will become u bar rho. Okay, so if we just replace that over here, partial rho by partial t, partial by partial x, and we have rho, the flux, rho u bar. If it is constant, then it is equal to 0. And we have partial rho by partial t, u bar, partial rho by partial x is equal to 0. So this is the advection equation for the density. But we want to make the velocity not as a constant but as a variable. Let me just remove that equation, and I start from here. And suppose that if we have flux, which is a function of density, then this will be equal to, if u is a variable, then it is u, not u bar. It means that u is unknown. It should be unknown quantity. So I put this value over here. We get partial rho by partial t plus partial by partial x. If I replace this flux with this quantity, then we have rho u is equal to 0. So you can see that we have a continuity equation. If I just open this again for you, this will be equal to partial rho by partial t plus partial by partial x rho u partial by partial y rho v partial by partial z rho w is equal to 0. So if I just remove these terms from the equation, we get the continuity equation. So this is another way to derive the continuity equation from the uh, from the model that we already discussed. In fluid mechanics, usually we derive this equation not in one dimension but in three dimension. We take a volume and we discuss inlet flow, outlet flow, then add it and we get the answer. This is another way we can do it as well. But here we just want to see how we can derive the continuity equation from this knowledge, from this. In the next video, I will talk about the momentum equation and we will discuss how the macroscopic and microscopic things uh, will make us to understand the momentum equation. Thank you for watching.